Reality might be a single thread in a vast cosmic tapestry. The multiverse theory proposes that every choice you make creates a new, parallel universe, and physicists are finding clues that these other worlds are leaving faint imprints on our own. By the end of this, you will see the universe in a completely new way, recognizing the subtle signs of other realities woven into the fabric of our own. We will investigate why the fundamental laws of physics seem so perfectly tuned for life, and what strange cosmic flows are pulling our galaxy toward an unseen horizon. How does the idea of infinite versions of yourself change what you believe is possible? Every possible path you could have taken is a real world somewhere else. Think of reality not as a single line but as an endlessly branching tree. Each decision, each random quantum event, causes the universe to split, creating a new, parallel branch for every possible outcome. This is the heart of the many worlds interpretation, a radical idea born in 1957 from the mind of physicist Hugh Everett. He was trying to solve a deep mystery in quantum mechanics, the strange rules that govern the smallest particles. The prevailing view, called the Copenhagen interpretation, said that a particle exists in a blurry cloud of possibilities until someone observes it, forcing it to choose a single state. But Everett asked a brilliant question. What if no choice is ever made? What if, instead of collapsing, every single possibility actually happens? In his view, the universe simply divides, each potential outcome becoming real in its own separate branch of reality. You are living in one branch right now, but in another, a different version of you made a different choice this morning. These worlds are not science fiction fantasies. As physicist David Deutsch has argued, the multiverse is not really a theory itself, but a direct consequence of our most successful scientific theories. It is what the math seems to be telling us. This vast, branching structure provides the very foundation for our next question. If these infinite worlds are real, however distant, could something from one of them ever leave a trace in ours? The search for an answer leads us to the bizarre and tiny realm where such leaks might begin. This strange connection between particles is called quantum entanglement. It is as if two coins, flipped on opposite sides of the galaxy, always land showing the same face, no matter the distance. Einstein famously called this spooky action at a distance because it seemed to defy the cosmic speed limit, the speed of light. How could information travel instantly between them? But what if the information is not traveling at all? Some physicists, like Sean Carroll, propose a breathtaking alternative. What if entangled particles are not communicating across a vast emptiness, but are, in fact, the very same particle existing in two different branches of the multiverse at once? In this view, their instantaneous connection is not a signal through space, but a fundamental link across realities. The random outcome we see when we measure one of them might not be random at all. It could be a direct result of its interaction with its other self in a parallel world. This would mean that every time a physicist conducts a quantum experiment, they are not just probing the fuzzy rules of our universe. They might be gently bumping up against the walls of a neighboring one. Every measured particle could be carrying faint imprints from its counterparts in realities just out of reach. If quantum experiments are our first delicate instruments for detecting this leakage, then our next clue comes from the oldest light in the cosmos, a fossilized glow from the dawn of time. That oldest light in the cosmos holds a secret fingerprint. Just after the Big Bang, the entire universe was a searing hot plasma, a dense fog of particles and energy. As it expanded and cooled, light was finally set free, racing across the cosmos for billions of years. We detect this light today as a faint, cold glow, the cosmic microwave background. It is a baby picture of the universe, and it should be almost perfectly smooth, a uniform sea of microwave radiation. But it is not. When scientists created detailed maps of this background, they found it was modeled with tiny hot and cold spots, like a cosmic fingerprint. Most of these variations fit our models of the early universe, but some do not. One of the most puzzling is called the axis of evil, a strange alignment of these hot and cold spots that suggests a preferred direction in space, as if the entire universe is tilted. This is a direct contradiction to the core principle of cosmology, that the universe should look the same in every direction. So what could cause such a fundamental anomaly? Theoretical physicist Laura Mersini-Houghton and others have proposed a breathtaking possibility. These irregularities could be bruises, imprints left from our infant universe brushing against another bubble universe in the vast multiverse. Imagine our cosmos as one bubble in a cosmic foam, inflating and expanding. In that dense foam, other bubbles are also growing. If two bubbles nudged each other in the first moments of creation, that collision would have sent shockwaves through the fabric of our reality, leaving a permanent scar in that first light. This is not just a wild guess. Sophisticated satellites like the Planck spacecraft have mapped the cosmic microwave background with incredible precision, and their data reveals strange, large-scale patterns that are difficult to explain with standard physics. Some of these patterns, especially in the polarization of the light, could be the specific signatures of such a cosmic collision, so the cold void of space may not be empty at all. It might be a canvas where other realities have left their mark. If the universe's oldest light can bear these scars, then what about the darkest objects we know? The places where the fabric of spacetime itself is tied into a knot. This brings us to the enigmatic role of black holes. At the edge of a black hole, the very concepts of space and time break down. An event horizon marks a boundary of no return, a point where the gravitational pull becomes so intense that nothing, not even light, can escape its clutches. These cosmic monsters seem like the ultimate endpoints, the universe's final trash compactors. But what if they are the opposite? Theoretical physics hints that black holes might not be endpoints at all, but gateways. Stephen Hawking's revolutionary work showed that black holes are not entirely black. They slowly leak energy, a faint whisper known as Hawking radiation. This evaporation process creates a deep puzzle, the black hole information paradox. If a black hole evaporates and vanishes, what happens to all the information about the stars and matter that fell into it? The fundamental laws of physics say information cannot be destroyed. So where does it go? One breathtaking possibility is that it does not go anywhere in our universe. The information could be funneled out, perhaps through a wormhole, a theoretical tunnel in spacetime that connects to another universe entirely. In this view, a black hole is not a pit, but a portal. Its surface might hold the key. The holographic principle suggests that all the information about everything that falls into a black hole is not lost inside, but is instead encoded on its two-dimensional event horizon, like a cosmic DVD. This information could then be projected outward, potentially into an entirely different dimension or a baby universe budding off from our own. If this is true, then the faint Hawking radiation leaking from a dying black hole might not be random static. It could be a scrambled broadcast, carrying encoded data from another reality. This idea transforms how we observe cosmic events. When two black holes collide, they send ripples through spacetime called gravitational waves. Our detectors like LIGO and Virgo listen for these ripples. Could a future, more sensitive instrument detect a strange anomaly in these waves? A subtle signature in the gravitational wave signal that does not fit our models could be the first clue. A faint echo from a collision that is not entirely of our world. Black holes challenge everything we know, and in doing so, they might just be the master keys to unlocking the existence of parallel worlds. To truly grasp the reality of these infinite realms, we must turn to the universal language that describes them, the cold, hard logic of mathematics. Mathematics gives us the language to map this infinite cosmic architecture, transforming the multiverse from a hazy idea into a structured possibility. Think of our entire universe not as an isolated expanse, but as a single three-dimensional membrane or brain, adrift in a much larger, higher-dimensional space. This is the core of brain theory, a concept that emerges from the deep waters of string theory and M-theory, which aim to unite gravity with the other fundamental forces of nature. In this view, our cosmos is just one sheet in a vast, multidimensional stack. Other brains, other entire universes, could be floating right alongside ours in this higher dimensional bulk, separated by a gap we cannot perceive. The distance between your hand and a parallel world might be infinitesimally small, but it exists in a direction our senses cannot point toward. This framework provides a stunningly elegant way for parallel realities to coexist without directly colliding. The sheer number of possible realities is almost incomprehensible. Physicist Leonard Susskind describes a cosmic landscape of perhaps 10 to the 500th power different universes. That is a number so vast it dwarfs the count of all the atoms in our observable universe. Each one of these potential worlds corresponds to a different vacuum state, a unique configuration of the fundamental constants that define reality. What we call the laws of physics, the strength of gravity, the mass of an electron, might not be universal laws at all. They could simply be local bylaws, the particular settings for our cosmic neighborhood. The mathematics that underpins this landscape involves intricate shapes known as Calabi-Yau manifolds. These are the hidden, curled-up dimensions of string theory, complex geometrical forms that determine how strings vibrate. The specific way these dimensions are folded dictates the properties of particles and forces in a given universe. It is a profound idea. The very reason our universe has the specific rules that allow for stars, planets, and life could be a simple accident of geometry, the way our particular brain is shaped and folded in the grand bulk of space. This mathematical structure also provides a mechanism for how these worlds might interact. If another brain universe drifted close to ours in the higher dimensional bulk, the gravitational pull between them could leave a detectable imprint on our cosmos. This could explain some of the strange, large-scale anomalies we see in the cosmic microwave background, as if our universe still bears the gravitational memory of a near miss with another reality. So mathematics does not just describe our single universe. It is increasingly pointing toward a far grander, multiversal architecture, a cosmic metropolis of which we inhabit just one street. If the rules of our reality are just one random draw from a near-infinite cosmic lottery, then the specific numbers that govern our existence become the next great mystery. Why do these fundamental constants have the precise values that they do? The precise settings of our universe seem almost too perfect. Consider the force of gravity. If it were just a fraction stronger, all stars would burn through their fuel in a cosmic flash, leaving no time for planets to form or life to evolve. If it were slightly weaker, matter would never have clumped together into stars and galaxies at all. The same goes for the strong nuclear force that binds atoms and the cosmological constant that drives the expansion of space. Tweak any of these numbers even a little, and the result is a dead, empty cosmos. This is the fine-tuning problem, a profound riddle that has puzzled scientists for decades. Why does our universe have such a specific, life-permitting recipe? One compelling answer is the Anthropic Principle. It suggests a simple yet staggering explanation. We find ourselves in a universe capable of supporting life because, in a vast multiverse containing every possible set of physical laws, we could not exist anywhere else. Our presence here is not a miracle, but a selection effect. We are simply living in one of the rare, habitable neighborhoods in an infinite cosmic metropolis. But what if the walls between these neighborhoods are not entirely solid? Astronomer John Webb and his team made a startling discovery while observing the light from distant quasars, the brilliant cores of ancient galaxies. As this light travels for billions of years across the cosmos, it passes through clouds of interstellar gas, which absorb specific colors or wavelengths, depending on the fine structure constant. This constant, known as alpha, governs the strength of electromagnetism. Webb's analysis suggested that billions of years ago, in certain directions of the sky, alpha might have been slightly different. It was as if the fundamental rules of chemistry were not quite the same in the distant past. If this evidence holds, it shatters the idea that our physical constants are truly constant. They could be slowly drifting, or perhaps they were imprinted with values from a different reality altogether. Imagine our universe as a room with a specific temperature and pressure. If a door to a much hotter room was left slightly ajar, our room would gradually warm up. In the same way, if our cosmos is nestled close to another universe with different physical laws, their fundamental constants could be subtly influencing our own, causing a faint, persistent drift in numbers we thought were fixed for all time. The search for this drift is now a primary goal for the world's most advanced instruments. Next-generation telescopes like the Extremely Large Telescope will peer back to the cosmic dawn, hunting for more clues in the light of the first stars. On Earth, networks of ultra-precise atomic clocks are being built to measure whether the flow of time itself, or the properties of atoms, are changing by unimaginably tiny amounts. The unsettling truth is that the stable ground of our physical reality might be an illusion, a temporary equilibrium shaped by invisible forces from beyond our cosmic horizon. This brings us to the greatest mystery of all, the strange force accelerating the expansion of our universe, dark energy. The accelerating expansion of our universe might be the most direct evidence for a multiverse. This mysterious force, dark energy, is not just pushing galaxies apart. It could be a faint echo from the very birth of reality itself. To understand this, we must rewind to the universe's first fraction of a second, to a period called cosmic inflation. The leading theory, pioneered by physicists like Alan Guth and Andre Linde, suggests that a bizarre energy field, a sort of anti-gravity, caused our entire cosmos to expand exponentially faster than the speed of light. But here is the crucial part. This inflation may not have been a one-time event that started and stopped everywhere at once. The theory of eternal inflation proposes that this process never truly ended. Instead, it continues eternally in a vast, ever-expanding background. In this picture, our entire observable universe is just one tiny bubble that formed when the inflationary field decayed in our local region, releasing its energy to create the hot soup of the Big Bang. But elsewhere, outside our bubble, inflation is still happening, and it is constantly spawning new bubble universes, each with its own unique set of physical laws. Our cosmos is just one froth in an infinite cosmic foam. This is where dark energy re-enters the story. The energy that drives the accelerated expansion of our universe today might be a leftover remnant, a faint shadow of that primordial inflationary field. Its curiously small value, a puzzle that has confounded physicists, might not be a fundamental constant at all. It could be an environmental accident, a value set by the specific way our bubble universe formed. Even more intriguingly, the strength of dark energy in our bubble could be subtly influenced by the presence of neighboring universes in the multiverse. If the walls between bubbles are not perfectly rigid, the vacuum energy from a nearby universe could be gently tugging on our own, setting our local value of dark energy to what we measure. This idea transforms how we observe the cosmos. When astronomers study distant supernovae to map the expansion history or chart the large-scale structure of galaxies, they are not just measuring the fate of our universe. They are potentially gathering clues about the multiverse environment we are embedded in. The precise way the expansion rate has changed over billions of years could hold a fingerprint, a sign that our cosmic bubble is not entirely isolated. So dark energy is more than a mysterious force. It could be a window. Understanding its true nature might finally reveal our specific address within an infinite cosmic metropolis. This search for subtle, multiversal signals is pushing science toward its next frontier, where the power of human intuition meets the raw calculation of machines that can think in multiple realities at once. The strange power of a quantum computer lies in its fundamental difference from any machine built before. Instead of using bits that are either a 0 or a 1, it uses quantum bits or qubits, which can exist as a 0, a 1, or both at the same time. This state, known as superposition, is like a coin spinning in midair, not yet decided between heads or tails. When multiple qubits are linked through quantum entanglement, their combined states create a vast landscape of simultaneous possibilities. A classical computer must check each path through a maze one by one, but a quantum computer can, in a sense, explore every single pathway at once. This allows it to solve certain complex problems, like simulating molecular interactions or breaking encryption, with a speed that defies classical logic. But where is this computation actually happening? Physicists like Michio Kaku have proposed a staggering idea. When a quantum computer evaluates all possible answers simultaneously, it might not just be processing information within our universe. It could be distributing the workload across the multiverse, with each parallel reality handling a different part of the calculation. The single, correct answer that emerges in our world would then be the result of a consensus reached across countless versions of the machine. This would explain the otherwise inexplicable efficiency. It would mean that by building a quantum computer, we have inadvertently constructed the first device capable of tapping into the collective processing power of infinite realities. Some of the most intriguing hints for this come from seemingly simple devices called quantum random number generators. These machines use quantum events, like the decay of a radioactive atom, to produce truly random sequences. Yet experiments have occasionally recorded strange statistical anomalies, brief patterns in the noise that should not be there. One interpretation is that we are witnessing subtle interference, a faint bleed through from a parallel world where the random sequence came out differently. To actively hunt for these leaks, scientists are designing sophisticated quantum experiments that run the same process thousands of times, searching for tiny inconsistencies. If the fundamental probabilities of quantum mechanics show even the slightest, most persistent deviations from the expected math, it could be a sign that we are not alone. The quantum world, with all its inherent weirdness, may be our most direct interface with the multiverse, turning advanced labs into listening posts for realities just beyond our own. And if modern technology can detect these faint echoes, it makes you wonder about the echoes from our past, the strange events that have baffled humanity for centuries. History is filled with whispers that sound like echoes from another room. Scattered throughout our ancient records are artifacts and ideas so advanced, so out of place, they seem to have fallen from the sky. The Antikythera mechanism, a complex bronze gearwork device recovered from a 2,000-year-old shipwreck, is a perfect example. This intricate astronomical calculator could predict planetary positions and eclipses with a sophistication that would not be seen again for over a millennium. Where did such knowledge come from, and why was it lost? The standard explanation involves brilliant, isolated genius, but another possibility is more radical. What if such objects are not entirely of our world? Could they be fragments of technology, or blueprints for knowledge, that somehow slipped through a temporary crack in reality from a parallel universe where science developed along a different path? This is not to say ancient aliens delivered them, but rather that the boundaries between worlds may be thin. allowing information to bleed through in rare, unpredictable events. Look at the flood myths found in cultures from Mesopotamia to the Americas, all describing a great deluge, or the uncanny similarities in creation stories that speak of multiple worlds or cycles of destruction and rebirth. These could be more than shared human imagination. Philosophers like Plato wrestled with the concept of ideal forms, perfect versions of things that exist in a realm beyond our own. These ancient intuitions bear a striking resemblance to the modern multiverse, a cosmos of infinite variations. If knowledge can cross the void between universes, it would not arrive as a clean data stream. It would come as a sudden, inexplicable insight, a dream of a machine that could not be built, a mathematical principle that defied the era. This would explain the sporadic nature of these historical leaps, periods of incredible innovation followed by long ages of stagnation. The knowledge was not developed here consistently, but was instead received in fleeting, unstable glimpses. The individuals who experienced these leaks might have been the visionaries and prophets of their time, gifted with concepts they could only partially understand or replicate. Examining our past with this lens does not rewrite history, but it might finally explain its greatest puzzles. It suggests that the human drive to explore and create is not just a product of our world, but is perhaps being subtly nudged by faint signals from a chorus of other realities. This age-old fascination with other worlds is no longer confined to myth and speculation. Today, that search has moved into the sterile, precise environment of the laboratory, where scientists are designing bold experiments to test these very ideas. Our most advanced machines are now hunting for ghosts in the data. At the Large Hadron Collider, scientists are not just smashing protons together to discover new particles. They are also searching for something far stranger, tiny violations of the universe's most sacred accounting rules. The conservation of energy and momentum are foundational principles, laws that say these quantities cannot be created or destroyed, only transformed. But what if, in a rare and fleeting moment, a particle collision seemed to lose a tiny amount of energy, or a particle appeared to gain momentum from nowhere? In our universe, this would be impossible. But if our three-dimensional brain briefly brushed against another parallel brain floating in the higher dimensional bulk, the gravitational tug from that other world could impart a tiny, measurable jolt to the particles in our detectors. The LHC's immense precision makes it a perfect instrument for this cosmic audit, scanning trillions of collisions for any anomaly that cannot be explained by the physics of our world alone. Meanwhile, in the silent, dark rooms of quantum optics labs, a different kind of search is underway. Here, researchers work with entangled photons, the very particles that exhibit spooky action at a distance. They run the same entanglement experiment thousands, even millions of times, building up a statistical map of the results. According to standard quantum mechanics, the outcomes should follow a very specific, predictable pattern of probabilities. But if there is any persistent, tiny deviation from this pattern, any slight skew in the statistics, it could be a monumental clue. This would suggest that the probabilities are not purely random, but are being ever so slightly influenced by interactions with other versions of the experiment running in parallel realities. It would be like hearing a faint, consistent hum of static in the background of a perfectly tuned radio signal, a hum that comes from another station on a different frequency. These modern tests build upon the brilliant thought experiments of the past. Physicist John Archibald Wheeler once conceived of a mind-bending scenario called the delayed choice quantum eraser. In this experiment, a particle like a photon seems to decide whether it traveled as a wave or a particle based on a measurement choice made after it has already completed its journey. This challenges our most basic intuition about cause and effect, suggesting that the present can rewrite the past. In a single universe, this is deeply paradoxical. But in a multiverse, it makes a strange kind of sense. The different measurement choices simply select which branch of reality we end up in, a branch where the particle's history was always consistent with that final observation. Laboratory versions of this experiment have been successfully conducted, and while they confirm the weirdness of quantum mechanics, they also open a door. Future, more complex variations might reveal effects that are completely inexplicable without the branching reality of the multiverse. These controlled environments are our best hope for turning philosophical speculation into hard, physical evidence. They force us to confront a profound question that reaches far beyond the laboratory walls. If these parallel selves are real, what does that say about the nature of your own choices, your identity, and the very meaning of your life? This infinite branching of realities forces a profound question about who you really are. If every choice spawns a new universe, then your identity is not a single, solid thing. It is a shimmering, ever-diverging constellation of possibilities. The philosopher David Lewis argued that all of these possible worlds are just as real as our own. They are not imaginary. They are concrete, physical places, simply disconnected from our space-time. In this view, the version of you reading this script is just one member of a vast and scattered family. The you who chose a different career, the you who took a different route to work, they are all out there, living their complete and equally valid lives. This challenges the very uniqueness of your experiences. That profound joy, that deep sorrow, that moment you thought was yours and yours alone, is being felt in some variation by countless other versions of you across the cosmic expanse. What does that do to our understanding of consciousness? Is your awareness a singular flame, or is it a flicker repeated endlessly across the multiverse, each one believing itself to be the only one? This directly confronts the ancient puzzle of free will. If every possible action is taken somewhere, does that mean our path was already written? Not necessarily. Your choices are still genuinely free. They are the mechanism that determines which branch of reality you will experience. The other branches are not predetermined destinies. They are the equally real outcomes of the choices your other selves freely made. This shifts the weight of responsibility in a strange way. Your decisions still matter immensely, but only to the specific thread of consciousness that is you. Your ethical choices define your corner of the multiverse. In an infinite cosmos, where every action is taken and every consequence unfolds, the value of a single good deed might feel diluted. Yet its value is not in its uniqueness, but in its authenticity within your own timeline. Choosing kindness in your world solidifies a reality where kindness prevails. It creates a branch of existence where that light exists, and that matters to everyone who shares that branch with you. Engaging with these ideas can be dizzying, but it can also be liberating. It reframes regret, not as a mistake that ruined a single, perfect life, but as a path not taken in your particular story, while another version of you explores its consequences elsewhere. Your life becomes one unique expression of a vast, interconnected tapestry. These philosophical ripples extend from the personal to the cosmological, challenging our understanding of the universe's very structure and leading us toward one of its greatest gravitational mysteries. These cosmic flows are pulling our entire galactic neighborhood toward an unknown horizon. For decades, astronomers have known that our Milky Way, along with countless other galaxies, is not moving randomly. We are all caught in a vast river, streaming toward a colossal, invisible mass known as the Great Attractor. It lurks behind the zone of avoidance, a region of our own galaxy's dust that blocks our view, making it a ghost in the cosmic machine. But the mystery deepens far beyond this single point. On an even grander scale, entire clusters of galaxies are drifting in a coordinated motion, a phenomenon astronomers call dark flow. It is as if a cosmic tide is pulling them in a specific direction, a current that should not exist if our universe is as uniform as we believe. These are not just curiosities. They are fundamental challenges to our model of the cosmos. Surveys like the Cosmic Flows Project have meticulously mapped the velocities of thousands of galaxies, creating a dynamic atlas of our cosmic neighborhood. The resulting map reveals these immense streams, like tracing the paths of leaves caught in a wind whose source we cannot see. The most breathtaking explanation is that this wind is blowing from another reality. If our universe is a bubble floating in a higher dimensional multiverse, it is not floating in perfect isolation. Neighboring bubble universes could be drifting nearby in the grand bulk of space. Even though they are separated from us by a fundamental barrier, their immense mass would still exert a gravitational pull. This force would act like a distant magnet, gently tugging on the entire structure of our cosmos and setting our galaxies adrift in a coherent flow. We would not see the source, just its gravitational footprint imprinted on the motion of everything we can observe. Researchers are now running sophisticated computer simulations to model how such an external gravitational pull would manifest. They are searching for specific patterns in the dark flow that match the predictions of multiverse cosmologies. Finding a match would be like discovering that the strange draft in your house is not a faulty window, but a permanent breeze from a door you never knew was there. This search transforms our understanding of these anomalies. The great attractor and dark flow are no longer just invisible masses or unexplained currents. They become potential signposts, pointing toward realities that lie forever beyond our observational horizon. If the gravitational pull of other worlds can influence galaxies, then perhaps something even more subtle can influence the mind. This leads us to a profound frontier, the possibility that consciousness itself might be a conduit for experiencing the multiverse. Your own mind might be a window into the multiverse. For decades, a fringe idea in physics has suggested that consciousness is not a passive observer but an active participant in shaping reality. The von Neumann-Wigner theory proposes a startling link, that the conscious act of observation is what forces a blurry quantum possibility to snap into a single, definite state. In a single universe, this places an immense, almost magical responsibility on the mind. But within the framework of the many worlds interpretation, it takes on a different, equally profound meaning. Your conscious awareness might not be collapsing possibilities at all. Instead, it could be the mechanism that selects which branch of reality you will experience. Every moment of waking life would be a continuous process of your consciousness navigating an infinite tree of possibilities, following one specific path while countless other versions of you follow the others. This shifts the question from what reality is to what awareness actually is. Could it be a fundamental force, a property of the cosmos that allows a single thread of experience to be woven from the vast tapestry of parallel worlds? This leads to an even more specific biological hypothesis. The renowned physicist Roger Penrose and anesthesiologist Stuart Hameroff proposed that the seat of consciousness might be found deep within your brain's neurons, in structures called microtubules. These tiny protein scaffolds could be more than just cellular supports. Penrose and Hameroff suggest they are quantum computers, where delicate superposition and entanglement occur, processes that are inherently connected to the multiverse. In their orchestrated objective reduction theory, these quantum computations in your brain reach a threshold and collapse. But this collapse is not just a random event. It is a moment of conscious experience, and it is guided by information from the multiverse itself. This would mean that your brain is not an isolated organ. It is a sophisticated receiver, constantly tuning into the faint signals of other realities. If this is true, then those fleeting, unexplainable moments of human experience suddenly take on new significance. A sudden flash of intuition, a solution to a problem that appears in a dream, or the uncanny sensation of déjà vu might not be glitches in your neural machinery. They could be moments of quantum interference, brief resonances with the knowledge or memories of another version of you in a parallel world. When you have a powerful feeling of having lived a moment before, it might be because, in a real and physical sense, you have. Another branch of your consciousness is experiencing that same event, and for an instant, the signals cross. This idea pushes science into the realm of the deeply personal. Researchers studying altered states of consciousness, from deep meditation to the effects of certain psychoactive substances, are gathering data that could test these boundaries. In these states, the brain's normal filtering mechanisms are subdued, and people often report feelings of interconnectedness, of accessing knowledge beyond themselves, or of vividly experiencing other lives. While these are subjective experiences, they might be the first clues. If a specific brain state can be consistently correlated with a sense of multiversal connection, it would provide a biological target, a specific pattern of neural activity to investigate as a potential interface. The human mind, therefore, might be the most sensitive detector we have. It is not a tool we can point at the sky, but one we carry within us, constantly sampling the fabric of reality and perhaps, just perhaps, occasionally picking up whispers from the other side. This intimate link between awareness and the cosmos forces us to confront the nature of time itself, and the one-way arrow that seems to govern our existence. Our experience of time may be a local phenomenon, not a universal law. You feel time flowing from past to future, an arrow that never reverses. This one-way street is dictated by the second law of thermodynamics, which states that entropy, a measure of disorder, always increases. A hot cup of coffee cools down, it never spontaneously heats up. A smashed glass does not reassemble itself. This relentless slide into disorder gives time its unmistakable direction. But why was the universe born in a state of such incredibly low entropy to begin with? Why was the past so orderly, setting the stage for time's arrow to fly? This is one of cosmology's deepest puzzles, and the answer might be written in the relationships between worlds. In a vast multiverse, the flow of time could be different in every branch. Some universes might be born with high entropy, where time has no clear direction from the start. Others might see their arrow of time periodically reverse. Physicist Sean Carroll suggests that our universe's exceptionally low initial entropy could be the result of a larger multiversal environment. Imagine our cosmos as a room that started spotlessly clean. This is not the most likely state. Most rooms are messy. But if our room is connected to a much larger, much more disordered house, then the overall entropy of the whole system is high, as the law demands. Our tidy room is just a rare, low-entropy fluctuation within a vastly more chaotic multiverse. This perspective reframes the origin of time itself. If this is true, then the walls between these rooms might not be perfectly sealed. The leakage of information or a subtle energy from a neighboring universe could, in theory, cause a local and temporary decrease in entropy in our own region. It would be like a gust of wind from outside briefly pushing the air in your room into a more ordered state. Such an event would create a noticeable anomaly in time's arrow. For a fleeting moment, the thermodynamic rules would seem to run in reverse. Scientists are actively looking for these fingerprints. They scrutinize the cosmic microwave background for patterns of polarization that suggest a primordial encounter with another reality. An encounter that could have imprinted our universe with its orderly beginning. In particle physics, teams meticulously measure the decay rates of unstable particles. These rates are governed by probability and entropy. If physicists ever found that the decay rate of a specific particle briefly and inexplicably changed, it could signal a momentary influx of order from beyond our spacetime. The very forward march of time, something we consider an absolute truth of our existence, might be a fragile condition, perpetually influenced by the invisible pull of other realities. This profound connection forces a radical question. If our reality is so permeable, Could the entire structure of our existence, including time and space, be the product of an even more fundamental process, a computation running on a cosmic scale? The most fundamental code of our reality might be written in the language of particle physics. When scientists probe the deepest levels of existence, they find nature is not infinitely divisible. There appears to be a smallest possible unit of space, a tiny pixel of reality known as the Planck length. It is about 1/trillionth of a trillionth the size of an atomic nucleus. Similarly, there is a smallest unit of time, the Planck time. These are not just small numbers, they are fundamental limits, a cosmic resolution beyond which the concepts of before and after, here and there, simply break down. Why would the universe have a resolution? In a purely natural cosmos, this is puzzling. But in a simulated reality, it makes perfect sense. Every computer simulation has a finite resolution, a limit to how much detail it can process and display. The Planck units could be the pixel size and processor clock speed of the universe we inhabit. This idea transforms how we view experiments at facilities like the Large Hadron Collider. When physicists accelerate particles to nearly the speed of light and smash them together, they are not just searching for new particles. They are stress testing the fabric of spacetime itself, pushing the simulation to its computational limits. Researchers have even proposed specific tests, like analyzing the patterns of high-energy cosmic rays. In any complex simulation, there are trade-offs between accuracy and processing power. A simulated universe might use shortcuts or approximations for very rare or energy-intensive events. If we ever detected a consistent pattern in particle collisions that violated our known laws of physics in a specific, computationally efficient way, it could be evidence of such a shortcut in the cosmic code. This is not just a wild speculation. The laws of physics we have discovered are remarkably mathematical. They can be expressed with elegant equations, as if written in a programming language. The constants of nature, like the speed of light, appear to be finely tuned parameters. In a simulated multiverse, each universe could be a separate instance running on the same cosmic hardware, each with its own slightly different settings file. This provides a stunningly simple explanation for the fine-tuning problem. Our universe is not miraculously tuned for life. It is simply one of countless simulation runs where the parameters, by pure chance, allowed for stars and planets to form. The leaks between these simulated worlds could then be understood as data corruption or network interference. When two complex simulations run on the same system, they can sometimes experience crosstalk, where data from one bleeds into the other. In our world, this might manifest as a ghostly particle that appears from nowhere, a brief fluctuation in a fundamental constant, or a statistical anomaly in a quantum experiment that defies all odds. These would be the cosmic equivalents of a software glitch, a momentary artifact revealing the digital machinery underneath our analog experience. The search is on for these artifacts. Scientists are meticulously analyzing data from particle colliders and deep space telescopes, looking for any recurring anomaly that suggests a constraint or a pattern more indicative of computation than of fundamental law. The goal is to find the universe's source code, not by reading it, but by watching for the moments it stutters. This technological perspective on existence leads to a final, deeply personal frontier: the nature of our own consciousness within this vast, potentially simulated multiverse. The elegant equations of the Standard Model have mapped the known particles and forces with breathtaking precision. Yet this masterpiece is fundamentally incomplete. It cannot account for the dark matter holding galaxies together, nor can it explain why ghostly neutrinos have any mass at all. These are not small gaps, they are chasms in our understanding, and the data is now pointing directly toward them. At the Fermi National Accelerator Laboratory, scientists have been meticulously measuring a property of the muon, a heavier cousin of the electron, known as its magnetic moment. According to the standard model, this value, called G-2, can be calculated with extreme accuracy, but the experiments tell a different story. The muon is wobbling just a little more than it should, as if an invisible hand is gently nudging it. This persistent anomaly, confirmed with greater and greater certainty, suggests the muon is sensing something the standard model does not include. It could be an unknown particle or a fifth fundamental force, flickering in and out of existence. But what if this phantom influence is not from our universe at all? Theorists propose that the fabric of our reality might be interwoven with extraspatial dimensions, realms curled up so tiny that we only perceive their effects as new forces or particles. These dimensions could be bridges connecting our world to a parallel one. In this view, the muon's strange wobble is not a flaw in our theory, but a tremor, a faint vibration transmitted across the dimensional divide from a reality operating under slightly different physical laws. The evidence extends beyond a single particle's dance. When physicists smash protons together at colossal speeds in machines like the Large Hadron Collider, they meticulously account for all the energy and debris. On rare occasions, a collision seems to be missing a tiny amount of energy. In our closed system, this is impossible. Energy must be conserved. But if a particle produced in that violent impact, a particle that interacts only with gravity, slipped out of our dimensional membrane and into the bulk of a higher dimensional space, it would vanish from our detectors, taking its energy with it. This missing energy could be the first direct signature of matter escaping our universe, a cosmic fugitive fleeing to another realm. These anomalies are not failures, they are guideposts. They are forcing physicists to build a deeper, more expansive theory, one where the three-dimensional stage we act upon is merely a slice of a far richer, multidimensional reality. The search for this ultimate framework is what leads us to listen for the most violent events in the cosmos, events that shake the very foundation of space-time and might carry echoes from beyond. The violent embrace of two black holes sends shivers through the cosmos, ripples in the very fabric of space-time we call gravitational waves. These are not sounds, but vibrations in reality itself, and our detectors on Earth have learned to listen. Each collision we record tells a story of mass and energy. But what if some of these stories are not entirely our own? If our universe is a membrane floating in a higher dimensional bulk, then a cataclysmic event in a parallel brane could also generate gravitational waves. These ripples would travel through the bulk, and when they washed against our universe, they would leave a faint, distinct signature in the signals we detect. Our current observatories like LIGO and Virgo are listening to the loud, nearby crashes, the thunderclaps of the cosmic symphony, but the future holds the promise of hearing the whispers. The Laser Interferometer Space Antenna, or LISA, is a planned observatory that will float in space, free from Earth's vibrations. It will be sensitive to a much lower frequency of gravitational waves, allowing it to tune into the background hum of the cosmos, a steady hiss from the earliest moments of creation. Within that primordial static, scientists hope to find a specific pattern, a chorus that includes the echoes of our universe's birth and, perhaps, the resonant crash of its first contact with another reality. What would such an anomaly look like? It could be a strange polarization in the waves, a twisting that does not match the predictions of general relativity for events in our universe alone. Or it could be a statistical pattern in the hum, a persistent signal that points to an external source, like hearing a conversation from the apartment next door through the walls. Every time we record a new gravitational wave, we are not just cataloging cosmic events, we are checking for cosmic accents, subtle inflections in the signal that suggest the event was influenced by physics from beyond our horizon. This new sense of hearing transforms our relationship with the cosmos. We are no longer just looking out at a silent film of stars, we are pressing our ears against the walls of reality, listening for the conversations happening in the rooms next door. This profound idea, that we might detect other worlds through their gravitational echoes, forces a deeply personal and unsettling question about our own place within this infinite tapestry. What does it mean for your own existence if every possible version of you is real? The concept of quantum immortality is a thought experiment that emerges directly from the many worlds interpretation, and it is as chilling as it is fascinating. It suggests that from your own subjective perspective, you can never experience your own death in a definitive way. Imagine a scenario where a marksman fires a bullet at your head. In one branch of reality, the bullet finds its mark, but in another, a quantum fluctuation deflects the bullet ever so slightly, or the gun misfires. Your conscious awareness, the thread of experience that is you, would follow the branch where you survive. This does not mean you are invincible. It means that you will only ever find yourself in a reality where a sequence of unlikely events conspired to keep you alive. You would inevitably experience a life filled with near misses and miraculous escapes, simply because you cannot experience the alternative. This logic extends to the very end of life. From your point of view, you might always find yourself in a universe where medical science discovers a cure for your illness just in time, or where a life-extending technology is developed before your natural lifespan ends. Your personal timeline would seem to stretch on, not because you are special, but because you are only aware of the branches where you continue to exist. This is not a comforting idea of eternal life, but a strange and isolating one. It paints a picture of a consciousness that continually branches away from death, eventually finding itself utterly alone in a universe that has grown cold and empty, a last observer in a fading reality. While this is a philosophical puzzle rather than a scientific theory, it highlights the profound implications of taking the multiverse seriously. It forces us to confront the nature of our own conscious experience, and asks whether the single, linear life we perceive is the entire story, or just the one thread we are holding. This unsettling thought experiment forces us to question the very nature of our life's narrative. Quantum immortality is not a promise of eternal youth, but a logical consequence of an infinite, branching reality. From your own subjective point of view, there might always be a path where you survive. Imagine a car accident, a sudden illness, or a fall from a great height. In countless branches, the outcome is fatal. But your conscious awareness, the thread of you, can only follow the single branch where a quantum fluctuation, a split-second decision, or a sheer miracle allowed you to live. You would never experience the terminal moment itself, only the timeline where you narrowly escaped it. This creates a bizarre form of survivor bias on a cosmic scale, where you inevitably find yourself in a reality that seems filled with near misses and inexplicable good fortune. While this is a deeply controversial and philosophical idea, it transforms how we might interpret those profound human stories of miraculous survival. An individual who walks away from a catastrophic event against all odds might describe a moment of expanded awareness, a feeling of seeing their life flash before their eyes, or a sensation of moving through a tunnel of light. From a multiverse perspective, these could be more than just neurological glitches. They might be fleeting moments of resonance, where your consciousness brushes against the memories or experiences of the other versions of you in the branches that did not survive. It is as if, for an instant, you perceive the entire tapestry of your existence, not just the single thread you are holding. This connection between abstract cosmology and intimate human experience adds a deeply personal dimension to the science. It suggests that our most profound personal mysteries might have roots in the fundamental architecture of reality. This search for a deeper, more fundamental process governing reality leads to an even grander evolutionary idea, one where universes themselves are born, live, and reproduce. The theory of cosmological natural selection proposes that our universe is not a unique, one-time event. but one member of a population of universes, all competing in a cosmic evolutionary tree. Just as natural selection on Earth favors organisms that are well adapted to reproduce, a cosmic version would favor universes that are finely tuned to create black holes, as these could be the seeds for new baby universes. In this breathtaking scenario, a universe that successfully produces many black holes is effectively a highly fit parent, giving birth to a multitude of offspring universes. These new universes would inherit their fundamental constants, their physical laws, from their parent, but with slight random variations like genetic mutations. Over countless generations, this process would select for universes that are exceptionally good at making black holes. This provides a powerful, non-miraculous explanation for the apparent fine-tuning we observe. Our universe is not fine-tuned for life. It is fine-tuned for black hole production, and we, as living beings made from stardust, are simply a fortunate byproduct of that cosmic selection pressure. The very laws that allow for stars to form, live, and die in supernova are the same laws that create the conditions for black holes. We exist because we live in a universe that is a champion at cosmic reproduction. This idea transforms black holes from mysterious endpoints into cosmic wombs, the engines of a grand, multiversal life cycle. Lee Smolin's theory reframes the entire cosmos as a living, breathing ecosystem. Cosmological natural selection proposes that universes are not static creations, but dynamic entities that live, reproduce, and evolve. In this breathtaking view, a black hole is not an end. It is a cosmic womb. When a star collapses into a black hole, the extreme conditions at its singularity might trigger the birth of an entirely new universe, budding off from our own. This new offspring universe would inherit its fundamental physical constants from its parent, but with slight, random variations, like genetic mutations in biology. Over countless generations, a form of cosmic evolution takes hold. Universes that are better at producing black holes will have more offspring, passing on their traits. This means the multiverse becomes populated with universes whose laws are perfectly optimized for one thing: creating stellar factories that inevitably lead to black holes. The fact that our universe also allows for planets and life could be a fortunate accident, a side effect of being fine-tuned for black hole production. The very strength of gravity and the nuclear forces that allow stars to form and die in supernova are the same laws that create these cosmic engines. This theory provides a powerful, non-miraculous explanation for the apparent fine-tuning we observe. We do not live in a special universe designed for life. We live in a universe that is a champion at cosmic reproduction. This framework transforms the multiverse from a static collection of worlds into a dynamic, evolving tree of life on the grandest possible scale. And just as genes can transfer between organisms on Earth, information might leak between these budding universes. A subtle gravitational nudge or a quantum fluctuation from a parent universe could influence the physical constants of its offspring, optimizing them for survival across generations. If this is true, then by studying the population of black holes in our cosmos and comparing the fundamental constants with extreme precision, we might one day find patterns, a cosmic family tree written in the laws of physics themselves. This evolutionary view of reality forces us to look forward, to consider our own potential role not just as inhabitants of a universe, but as potential actors within its grand, unfolding story. Our future as a species may be deeply intertwined with this cosmic life cycle. The same quantum whispers that hint at other realities might one day be amplified into a roar, powering our civilization. Imagine a future power plant that does not burn fuel, but instead taps into the vast energy gradients between our universe and a neighboring one. The vacuum of space is not truly empty. It seethes with quantum fluctuations, particles and antiparticles blinking in and out of existence. If our cosmos is nestled against another with a slightly different vacuum energy, that boundary could be a source of immense potential, like a cosmic dam waiting to be opened. Theoretical devices, often called Casimir engines, could theoretically harness this energy, drawing power from the silent pressure of parallel worlds. This is not about stealing energy, but about channeling a natural flow that already exists, turning a faint leak into a sustainable current. The implications for space travel are even more profound. The Alcubierre warp drive, a concept for faster-than-light travel, requires exotic matter with negative energy density to warp spacetime into a bubble. Such matter may be impossible to find in our universe, but what if it is commonplace in another? A future spacecraft might not carry its own fuel, but instead use a multiversal interface to borrow the necessary physical laws from a reality where warp travel is simple, effectively surfing on borrowed physics. We are already taking the first steps toward this with quantum computing. These machines, by their very nature, might be primitive multiversal communicators. Researchers are exploring how to use entangled qubits not just for calculation, but to send simple, non-random signals. A message sent this way would not travel through space, but would simply be read out in a parallel world, a form of communication that is instantaneous and utterly secure. Yet this breathtaking potential is shadowed by profound ethical questions. If we can draw energy from another universe, are we destabilizing it? If we send a message, are we an unwelcome intrusion into a world that has developed in its own unique way? The act of observation in quantum mechanics already influences the system. So what kind of impact would a deliberate, amplified signal have? The pursuit of these technologies is not just an engineering challenge, it is a philosophical one, forcing us to consider our responsibilities as citizens of a much larger cosmos. This drive to reach across the void has always been a part of us, long before we had the equations to describe it. It finds its voice not only in laboratories, but in the stories we tell and the art we create. Our most enduring stories are filled with doors to other worlds. Long before physicists wrote equations for the multiverse, writers and artists were mapping its strange terrain. Jorge Luis Borges, in his short story The Garden of Forking Paths, described a novel that was itself a labyrinth, where every possible outcome of an event branches into a new, coexisting reality. This was not just a literary device. It was a prescient vision of the many worlds interpretation, crafted decades before Hugh Everett gave it a scientific name. These creators were not merely fantasizing. They might have been tuning into a frequency, intuitively sensing the same cosmic architecture that science is now beginning to quantify. When a concept appears simultaneously in the labs of physicists and the studios of artists, it suggests a shared inspiration, a whisper from the walls of reality that some minds are uniquely equipped to hear. The explosive popularity of multiverse narratives in modern cinema, from the sprawling adventures of Marvel to the poignant family drama of Everything Everywhere All at Once, taps into a deep, collective curiosity. These stories resonate because they give form to our unspoken suspicions that our lives are just one version of a much grander story. They provide an emotional vocabulary for the dizzying idea that every choice we make creates a new world. Art becomes the testing ground for the philosophical and personal implications of a multiverse, allowing us to safely explore questions of identity, regret, and destiny. A painter might blend colors in an impossible gradient. A musician might compose a chord that feels both familiar and alien. And a novelist might craft a character who remembers a life they never lived. In doing so, they are not just creating fiction. They could be documenting faint impressions, translating subtle leaks from parallel realities into a form our shared consciousness can understand and embrace. This cultural record is a vital counterpart to the hard data. reminding us that the search for other worlds is not just a scientific endeavor, but a deeply human one. It prepares us for the profound responsibilities that come with this knowledge, forcing us to ask what happens when we stop just listening for these echoes and start trying to answer back. The act of observation itself may be the first step across a threshold we cannot close again. Our growing ability to detect the multiverse carries a profound and unsettling responsibility. If these other realms are not empty, but teem with their own forms of sentient life, then every experiment we conduct, every signal we send, could ripple across realities with consequences we cannot foresee. The very act of observation, which in quantum mechanics seems to influence a system, might be a form of interference on a cosmic scale. What if our search for energy, tapping into the vacuum between worlds, inadvertently drains a resource vital for another civilization's survival? Or what if a message we broadcast into the quantum void is received as a terrifying, unnatural phenomenon in a less technologically advanced universe? Philosophers grappling with these questions suggest that cosmic ethics must extend beyond our own spacetime. If a parallel version of you is a real, conscious being, do they possess inherent rights? Does their existence impose a duty upon you to act in ways that do not cause them harm, even if you never meet? The concept becomes even more complex when considering the potential for manipulation. If we ever learn to control these leaks, the power to influence entire realities would rest in our hands. Would it be ethical to nudge the physical constants of a neighboring universe to make it more hospitable for our own expansion, even if that fundamentally alters or destroys the life that evolved there under different rules? This is not a distant abstraction. The drive to explore is a fundamental part of our nature, but it must be paired with a framework for responsible exploration. Ethics becomes the essential compass for navigating an infinite cosmos, ensuring that our curiosity is guided by wisdom rather than mere ambition. As we push the boundaries of what is observable, we must also confront the inherent limits of our own perception, the final frontier where science meets the ultimate constraints of reality itself. The ultimate test for any scientific idea is whether we can find evidence for it. Yet the multiverse seems to deliberately hide from our gaze. This creates a deep philosophical rift within the scientific community. Critics argue that if a theory describes realms forever beyond our observational horizon, it ceases to be science and enters the realm of metaphysics. How can you ever prove or disprove something you cannot, by definition, interact with? Proponents counter that we are not completely blind. They point to the same cosmic clues we have explored, like the strange alignments in the cosmic microwave background or the inexplicable dark flow of galaxies. These are not proof, but they are hints, anomalies that the multiverse elegantly explains where standard models struggle. The true scientific challenge is not merely finding evidence, but designing experiments that can definitively distinguish a multiverse signature from something more mundane. A cold spot in the cosmic background could be a bruise from a colliding bubble universe, or it could be a statistical fluke, a simple cosmic coincidence. Isolating the true cause requires a level of precision and a volume of data that we are only now beginning to approach. This inherent limitation, however, is not a dead end. It is a catalyst. The very impossibility of directly seeing another universe forces a revolution in our methods, pushing us to build more sensitive telescopes and more precise quantum sensors. It demands a new kind of scientific humility, an acknowledgement that some of nature's grandest truths may only reveal themselves through their faintest, most indirect echoes. This framing is crucial because it shifts the multiverse from a question of certain proof to a matter of probability and inference. We are left to weigh the likelihood, to ask whether the growing pile of cosmic coincidences is just a run of good luck, or something far more significant. This naturally leads us to the mathematics of chance, and the role it plays in a cosmos of infinite possibilities. Probability itself might be a ghost from another dimension. In our familiar world, we think of chance as the roll of a dice, a 1 in 6 possibility for any number. But in a multiverse, that dice roll does not have a single outcome. It has 6. When you throw the dice, the universe splits, and in 6 separate branches of reality, each number lands face up. Probability, then, is not a measure of what will happen, but a measure of which branch you will find yourself in. Your conscious experience follows just one path through the infinite tree of possibilities. This radically reshapes our understanding of everything from a lottery win to the decay of a radioactive atom. A seemingly random quantum event in a lab might not be random at all, but a direct result of its entangled connection to its other selves in parallel worlds. If leaks between these worlds are possible, the implications are staggering. The subtle gravitational tug or quantum interference from a neighboring reality could nudge the odds, making certain outcomes in our universe slightly more frequent than pure chance would allow. This would create a persistent, faint skew in the statistics, a bias in the cosmic dice. Statisticians and physicists are now collaborating to explore how multiverse theories could revolutionize probabilistic reasoning in fields like finance and risk assessment. In the stock market, a seemingly unpredictable crash or boom might be influenced by economic decisions made in parallel worlds, their gravitational echoes subtly shifting investor sentiment on a mass scale. For insurance companies modeling the risk of a catastrophic event, the calculations become infinitely more complex if the event is not just unlikely, but is guaranteed to happen in a nearby universe with potential for cross-dimensional fallout. Rethinking randomness through this lens is not just a philosophical exercise, it opens new avenues for insight across countless disciplines. The very fabric of probability becomes a potential window, a sensitive instrument for detecting the structure and influence of the multiverse. As we pull together all these threads, from quantum anomalies to cosmic flows, a startling picture of our place in the cosmos begins to emerge. The scattered clues from across the cosmos are beginning to form a startlingly coherent picture. Quantum entanglement, the strange alignment of ancient light, the ghostly pull of dark flow. Each of these anomalies is a single piece of a vast, interconnected puzzle. On their own, they are curiosities, but together, they weave a narrative that our universe is not a solitary island. They point toward a cosmos that is porous, a reality whose borders are subtly permeable. No single observation serves as definitive proof. Yet the consistency across such wildly different fields of science is what makes the case so compelling. It is the difference between finding one fingerprint and finding the same fingerprint at multiple, unrelated crime scenes. The story they tell is one of connection. Physicists are now building unified models where this leakage is not a bizarre exception, but a fundamental feature of reality. These frameworks treat our cosmos as a dynamic participant in a far larger community of worlds, constantly exchanging faint whispers of information and influence through quantum channels and gravitational tides. This synthesis transforms the multiverse from a speculative thought experiment into a working hypothesis, the best available explanation for the collective oddities our instruments keep recording. We are moving from a collection of strange facts toward a deeper, more holistic understanding of existence itself, one where the walls between worlds are not solid barriers, but shimmering veils. This journey through the evidence culminates in a single, profound shift in perspective, a final thought on what it means to live in a universe that is forever touching others. Our exploration has revealed a cosmos far more porous and interconnected than we ever dared to believe. From the spooky whispers of quantum entanglement to the gravitational tides pulling at entire galaxies, these are not isolated oddities. They are threads in a single, breathtaking tapestry, hinting that our reality is just one vibrant thread in an infinite weave. The evidence challenges us to fundamentally expand our perception of existence, to embrace the staggering possibility that we are part of a grand cosmic community. As Carl Sagan so beautifully reminded us somewhere, something incredible is waiting to be known. That somewhere might not be a distant star, but a reality just beyond a veil we are only now learning to perceive. The pursuit of these mysteries does more than advance science. It rekindles a primal sense of wonder, reminding us that the universe is stranger and more magnificent than our everyday lives suggest. I would love to hear how these ideas resonate with you. What possibilities do they open in your own mind? Share your thoughts in the comments below. And if this journey into the fabric of reality intrigued you, subscribe for more deep dives into the cosmos's greatest secrets. Thank you for joining me in uncovering how our world might be a single room in an infinite mansion, filled with whispers from the hall.